Welcome back. We continue with data flow coverage criteria in week 3. Now, last time we defined what data flow was and what is the definition of a particular data, what is the use of a particular data, what is a DU path. Now, based on these definitions, we are actually going to see coverage criteria that work with these data flow definitions. So we define data flow coverage criteria as a set of DU paths that take a variable value from its definition through its use as the program executes using a sequence of statements. And sometimes for large programs, typically they tend to be large, there could be many variables. They could be defined and redefined at several different places, and there could be several different DU paths. So by looking at criteria, it helps to group the criteria using some way or the other. So we are going to take the DU paths that take variables from definitions to use and group the DU paths in some way or the other to define data flow coverage criteria. How are we going to group them? We are going to group them like this. So we first take a variable, let's say one particular variable, fix it, let's say variable v, and consider all the DU paths for that variable from a particular given node. So that is, the variable is v, the node is ni, and I'm going to consider all the DU paths that begin at that node for the variable v. We call a def path set, short form for definition path set, write it as DUNIV as the set of all DU paths with respect to the variable v that start at this node ni. We had already fixed the variable v. We are considering all the DU paths for the variable v that begin at the node ni. As I told you, for large programs, such number of paths can be large, so we group them once again. We might want to group them by uses, but it's typically not done in software testing. And when we look at examples, it will become clear to you why we don't group them by uses. So take a def path set like this. That is for a variable v, all the DU paths that begin at a particular node ni. So we group DU paths by definition and by use, and this will allow the definitions of the DU paths to flow over to its use as a program executes. Such a grouping is called a def pair set, so short form for definition pair set. For definition pair set DU, the same V is there, same NI is there. Now we fix a end node NJ. So DU NI NJ V is the set of all DU paths with reference to the variable V that starts at node NI and ends at node NJ. That's the def pair set. So a def pair set basically collects together all the ways to get from the definition of a particular variable V to a given use of the same variable at a particular node ni. A def pair set for a definition at node ni is nothing but the union of all the def path sets for that definition as they come in different places of different uses that vary over nj. That is, consider variable v that is defined at ni and consider all possible uses that end at nj. So that is du ni njv and take its union over all such nj. Then we get this entire def path set. We'll go back and look at the same pattern matching example. I'm not showing you the code once again. It was there in the last lecture. We'll directly consider the data flow graph of the pattern matching example. The data flow graph is given to you here in this slide. What is happening here? If you see the same CFG with augmented with definitions and uses. I'm going to illustrate to you what these two definitions are now on this example. What is a def pair set and what is a def path set? So for illustrating that, let's take the same pattern matching example and look at one definition of, let's say, I sub at node 10. So where is node 10 in this figure? It's here. and a variable I sub index over subject is defined here. It's also used here, but it's used in several other places. Can you spot one more use of the same variable somewhere else down the control flow graph? So let's say 10, there is a path back to 3, and there is a use here in the edge 3, 4 of this variable I sub. And then there is another use in the edge 4, 5 of the same variable I sub. There is one more use in the edge 5 of I sub, and there is one more use here down below in the edge 7 to 9. You're able to understand? So go from 10 to, take this back edge, go from 10 to 3, 3 to 4 edge, there's a use, 4 to 5, there's a use again. At the node 5, there's a use, and then go 5, 6, 7, the edge 7 to 8, there is one more use of this variable I sub that is defined at 10. So that's what is basically listed in this slide. In this example, we just saw that there was a definition of I sub at node 10. If I collect the DU path set for I sub at node 10, then this whole thing would be the set. This one that goes from 10 to the edge 3, 4, as we saw, 10 to the edge 3, 4 to the definition at node 5, and then down to all the way to 6, 7, 8, 6, 7, 9, and then back to 10 in two different ways, three different ways, right? So this is the whole thing, which is the DU path set. I can break this DU path set by grouping together. So here, what did I consider? I considered the variable V was I sub, and the node that I began in was 10, right? So this is DU NI V, and various ends uses at various ends were listed here. Now I can break down the uses also. So I can say du 10 for I sub. This is for the variable I sub. The definition is at 10. The use is at node 4. That is this du path 10 to 3 to 4. For the same variable I sub, definition at node 10 ends in the use at 5 in the du path 10 to 3 to 4 to 5. For the variable I sub, the definition at node 10 ends in the use at node 8 through this path, du path 10, 3, 4, 5, 6, 7, 8, and so on. I've just basically taken this set above here, the set of DU paths for I sub that begin at node 10, and broken it down into the set of DU paths for I sub that begin at node 10 and end at all these various nodes. So if I take the union of all these paths here, I get the set above here. That's what is given here in this definition. Def pair set and def path set. So is it clear? Basically, there is nothing, no magic here. You take a variable, take a particular definition of a variable at a particular node. If you consider all possible DU paths, then you consider all possible uses ending at all possible nodes. Or you could say for this variable with the definition beginning at this node, I consider use at a particular node nj, and that becomes a def pair set. So this is another kind of grouping. So let me go back down below. Now we are ready to define data flow coverage criteria. So sometimes you remember when we did structural coverage criteria, to make prime path coverage especially feasible, we had to sometimes look at side trips and detours. Here also, we can look at side trips and detours. In graph coverage, always side trips and detours are permitted to make coverage criteria look feasible. So a test path P is set to du tour a subpath D with reference to a variable V if the path P towards D in the portion of P to which D corresponds to in a def clear way as far as variable V is concerned. It's the same thing, it's the same touring. We just ensure that as far as V is concerned, it doesn't get redefined along the detour. Same thing for side trips also. We ensure that it stays definition clear as far as the side trip is concerned. Otherwise, we allow both side trips and detours as far as they don't redefine the variable V that we are focusing under. What are the three data flow criteria? They're very simple. Data flow is all about for a variable what its definition is, what its use is, and the flow of the value of the variable from the definition to the use. The data flow criteria also talk about the same thing. The three common data flow criteria are: first one, test requirement. Each definition reaches at least one use. It doesn't go waste. Every variable that is defined is used somewhere at least. So write a test case that ensures that every definition reaches at least one use of that variable. So that is the simplest data flow test requirement. The next one is more ambitious. It says every definition of every variable, write test cases that reach all possible uses. So your test requirement is each definition reaches all possible uses. The third TR says each definition reaches not only all possible uses, but it reaches all possible uses through all possible DU paths. Meaning, so you could reach the same use through different paths, right? Let me just go back and show you this example. If you take this last one, no, the definition at 10 reaches the use at 10 for the variable I sub through three different paths. Is that clear? So what the test requirement says is take all the three paths. That's all the third test requirement says. So to summarize, there are three data flow coverage criteria. First one, test requirement says every definition reaches at least one use. Second one says every definition reaches all possible uses. Third one says every definition reaches all possible uses through all possible DU paths. And as I told you just in the previous slide, if you encounter any of these test requirements to become infeasible, allow side trips and detours as long as they are definition clear. The same data flow criteria that I have defined formally in this slide, all definitions coverage test requirement says for each def path set du of the variable v at the statement n, tr contains at least one path d in S. All uses coverage says for each def pair set DUNINJV, TR contains at least one path D in the set S. That is, at least one definition in NI to at least one use in NG. All DU paths coverage says for each def pair set DUNINJV, TR contains every path D in the set S. So the first test requirement says every definition reaches at least one use. Second test requirement, all uses says every definition reaches all the uses. Third requirement, all DU paths says every definition reaches all the uses through all possible paths. I hope the three data flow coverage criteria definitions are clear to all of you. So if you remember, we had this simple example in the last lecture when we introduced data flow coverage criteria, where X was defined at the node 1, Z was defined at nodes 5 and 6, and X was used at nodes 5 and 6. So if I have to achieve coverage criteria just for the small example, if I have to say all definitions for X, that is, every definition reaches at least one use. So the test path would be begin at node 1, X is defined here, and maybe go through node 5 or node 6. So in this example, we've gone through node 6, 1 to 2 to 4 to 6 to 7 will ensure that the definition of X at 1 reaches at least one use, which is at 6. All uses says the definition of X at 1 should reach all the possible uses for X, which are the two uses for X, one at node 5, one at node 6. So all uses test requirement for X, the test paths are 1, 2, 3, 4, the use at 5 ending at 7, and 1, 2, 3, 4, the use at 6 ending at 7. Is this clear? Alternatively, you could consider 1, 3, 4, 6, 7 also. The third one, in fact, does that. Third one is the strongest data flow coverage criteria. all du paths for x. That is, you go from a definition of x to all possible uses of x through all possible paths. So to reiterate, definition for x is at node 1 and the uses are at node 5 and 6. And all du paths test requirement basically lists the four possible paths that take you from the definition of x to the uses uh, at 5 and 6. So the four paths are 1, 2, 4, 5, 7, 1, 3, 4, 5, 7. Similarly, 1, 2, 4, 6, and 7, and 1, 3, 4, 6, and 7. Is it clear? So let me just summarize it quickly. This slide is a useful summary. Three kinds of data flow coverage criteria requirement. Every definition reaches at least one use. Every definition reaches all possible uses. But in the second case, I don't worry about which is the path that I take. In the third case, I worry about that. I say every definition reaches all possible uses through all possible paths. That's what is the third test requirement. Is this clear? So let's go down. Yeah, now is the time to look at subsumption. If you remember, when we had looked at structural graph coverage criteria last week, these were all the coverage criteria that we looked at purely based on the CFG node, edge coverage, edge pair coverage, prime path coverage, then complete path coverage, and then we had round trips, simple round trip and complete round trip, right? So this is just a recap of what we saw earlier. Now we saw three new data flow coverage criteria, right? So we will first see how they subsume each other. Before we see how they subsume each other, a small set of assumptions are important to make sure that we don't get anything unsolved. So the subsumption results for data flow coverage criteria are based on three assumptions. One is we assume that every use of a variable is preceded by a definition of the variable somewhere. Obviously, if a variable is going to be used, it has to be first be defined. Otherwise, even a compiler will catch the problem. So we assume that. We also assume that every variable that is defined reaches at least one use. It's not left unused at all. We assume that this property holds. And the next assumption is if I have a node in the control flow graph with multiple outgoing edges, then at least one variable is used in each of the outgoing edge and the same variables are used on each out edge. I should be able to get the set of variables that are used in the outgoing edges. These are simple assumptions that I need before I look at data flow coverage criteria and subsumption. So the subsumption is fairly easy to see because the simplest would be what every definition reaches at least one use. So, which means if I satisfy all uses criteria, that is, every definition reaches all possible uses, then I know that every definition reaches at least one use. So, it obviously subsumes all defs criteria. Similarly, if I satisfy all DU paths criteria, that is, every definition reaches every possible use through every possible path, then I'm obviously including all uses criteria. So this picture should be fairly clear. All DU paths coverage is the most expressive data flow criteria. It just basically says for a variable, take its definition, take all possible uses, and take all possible paths that go through various uses. This is going to subsume all uses coverage, which in turn is going to subsume every definition reaching at least one use. That is all defs coverage. So this is one picture of data flow coverage criteria subsumption. And this is the other diagram of structural coverage criteria subsumption. They both work on same control flow graph. One considers the data flow information, one ignores the data flow information. Now, can we compare these two coverage criteria and say how structural coverage criteria compares to data flow coverage criteria? That's what we would like to see. So each edge of a graph is based on satisfying some predicate, right? Especially if I have if and while statement, the relational logical expression in that is going to be true or false. So each edge will have at least one use. There's going to be a predicate which uses a variable, makes it positive or negative, tests for it, and all that stuff. So definitely, if I do all uses data flow coverage criteria, I will do edge coverage criteria for sure. Similarly, because of my assumption that each DU path is a simple path, remember we had that condition in the definition of a DU path? Prime path coverage is also simple paths. So DU paths are simple paths. So prime path coverage, surprisingly, subsumes all DU path coverage. So prime path coverage is a powerful coverage criteria. So what I've basically done in this figure is put the two graphs together, I mean, two diagrams together. So let's see what it is. Let me just go back and to start with, we had this structural coverage criteria purely based on structure. Keep this diagram, the subsumption that you see in this slide in your mind. Then this lecture, we introduced data flow coverage criteria, which had this obvious subsumption relation. And then we made a few observations, how these two compare. This diagram summarizes everything. So it says prime path coverage here subsumes all DU path coverage. Is this clear? Because why? Simple assumption that every DU path is a simple path. Prime paths are maximal simple paths. So it will subsume. Independently, we saw all uses coverage subsumes edge coverage. Is this clear? So that is this new arrow that you see. And this one is this new arrow that you see. Otherwise, these three blobs here are the data flow coverage criteria. The rest of these coverage criteria are structural coverage criteria. I've just put them together with our new observation about what subsumes what. So this is a summary slide on how the various graph coverage criteria that we saw till now, structural and data flow, what subsumes what. So from this picture, it is very clear that if I am able to draw the control flow graph and achieve prime path coverage as a test requirement, then I would have successfully done several other coverage criteria. It's a very expressive coverage criteria. Sometimes it might get difficult to enumerate all prime paths, so we might be done with doing smaller coverage criteria like all uses or edge coverage or all DU paths and things like that. But if you can do prime path coverage, then basically you've subsumed several other coverage criteria. That's what it means. So data flow testing is actually a lot of work because you need the program, you need to generate the CFG, then you need to do this process called data flow analysis. We may not be doing too much of data flow analysis in this course. I'll teach you a bit about it when we move later because without doing the data flow analysis, for large pieces of program, it's difficult to take the control flow graph and augment it with definitions and uses of variables and get this DU pair set automatically. You need some amount of automation uh, processes to be able to take the input program, generate the control flow graph, augment it with definitions and uses, and get your DU pairs. Once you have your DU pairs, to get the test data generation also needs some work. And then you can measure whether coverage criteria is satisfied or not and get your test cases. We may not look at precise algorithms for this because these will involve sophisticated program analysis techniques. But there are several algorithms for generating DU pairs and for generating test data generation. You can do explicit search, which is what I illustrated to you. You can get test data using random testing. We will see a bit of this later in the course. You can get the test data using symbolic execution. Symbolic execution is a very powerful testing technique, so we'll spend a lot of time later in this course. You can also use another technique called model checking. So these various techniques, one after the other, we'll see a subset of them, especially random testing and symbolic execution. That will help you to get data flow test cases. If you would like to know a little more on how data flow coverage criteria work, here are some reference papers that you can study. They are very readable. This is a survey paper, so it has a lot of references. So I'll stop here. We'll continue with data flow testing in the next. Thank you.